this. All right. Happy Thursday. I won't get to see you again until next Thursday because we don't have class on Tuesday. It's kind of like a weird long weekend, not really long weekend because you don't have Monday off, but maybe you do. You don't have Monday classes, I guess. All right. So we're going to keep going in chapter 3, probability. And we're going to wrap up section 1 and then move pretty quickly into section 2, which is conditional probability. So in terms of review, I kept the kind of the excerpt. Oh, I forgot to bring the extra formula sheets. Sorry about that. Usually I bring them. I was kind of in a rush. Oh well, it's on Moodle. I'll bring them next time. Next week, I guess. So for our review, it was just on Tuesday, so we won't need a ton of review, right? Because you remember all this. Mostly our chatty Cathy's in the back there. Probabilities have to be between 0 and 1. It's the most important part, right? And then we've got our sample space. Our sample space is the set of all possible outcomes. Right? We have to consider all possible outcomes. That also helps us determine what the probability will be usually, okay, if it's not given. But the probability of the sample space, something of the possible outcomes happening, has to be 1, right? Which means if I add them all up, they have to add to 1. Using that fact, the probability of the complement of A must be 1 minus the probability of it happening, right? The probability of A. And we'll see that again today, so that's why I'm not reviewing it terribly. We did talk about the addition rule. Okay? The addition rule is if you are able to translate a word problem into the probability of A or B, okay? Or means addition. Okay? And so what you have is the probability of A plus the probability of B, but then remember you have to subtract the overlap. And as another reminder, if A and B are disjoint, right, visually there's no overlap, right, then the probability of A and B happening together must be 0. So then you would be subtracting 0, but that brings you down to a special case. Right? So if you always use this equation, then you're safe. And I can give you any 3 of these 4 components and ask you to find the 4th. Right? Today, well, last day we introduced independent events. So today we're going to focus on dependent events. Now, what I wanted to point out is that, so we can kind of ignore the dependent events for just a little bit longer, and we'll focus on the conditional probability section. Notice though, if you, okay, fine, I've got a couple of things to say here. Notice that if you have the probability of A given B, which we learned how to read last day, but again, we'll see it more today. The vertical line you read as given. So the probability of A given B is the probability of A and B. Oops. Oh, what a mess. And B divided by the probability of B. Now, if you multiply the probability of B over to the left-hand side and swing it around, what do you get? You end up here. The probability of A given B times B, or the probability of B, right, is the probability of A and B. Okay? And so in my mind, you don't really need this part because we'll use this equation always. Yeah? So if you're like me and you prefer to have fewer formulas and you can kind of massage them to what you need them to be, then that's what you can do. You can ignore this little section here and only use this one, right? And massage it to whatever you need it to be. Yeah? Okay. One thing I wanted to add to last day was, by definition, if A and B are independent, then what do we know? We know that the probability of A given B, well, knowing B doesn't affect the probability of A, right? And vice versa. So then we get the probability of A times the probability of B if they're independent. Yeah? And so one of the ways that we use this formula is not usually to find the probability of A and B, the probability of A and B. It's to confirm if A and B are independent or not. And so we often use this fact to determine if A and B, and B are independent. How? What you're going to do is you're going to check if the probability of A and B, does it equal the probability of A times the probability of B? In this scenario, I would need to give you all three of those probabilities. Okay? If they end up being exactly the same, and they have to be exactly the same, then you can say that they are independent. Okay? So it's kind of a neat kind of roundabout trick to see if two events are independent. Now here, they must be exactly equal in order to be independent. As a quick example, if the probability of A is 0.6, the probability of B, I'm just making these up, is 0.2, and the probability of A and B is, I don't know, 0.5. Squeeze that in here. Yeah. Are A and B independent? Who's this little guy? So, how will we know? Well, if they are independent, then the probability of A and B is equal to the probability of A times the probability of B. Now we have all those components. So really, what we would need to know is if 0.5, is it equal to 0.6 times 0.2? I don't think so. Well, let's confirm. 0.6 times 0.2, I get 0.12, which is not equal to 0.5. So A and B are not independent. And that's a reason why, unless you know they're independent, you don't want to jump into multiplying them together unless you know that they're independent, right? And so therefore, A and B are not independent events. Ugh. Nice. up here on Thursday. Well, we're here on Thursday. So let's do this thing. A recent Gallup poll. Gallup does a ton of research, a ton of surveys, and so a Gallup poll suggests that 25.5% of Texans do not have health insurance as of June 2012, so quite old, I guess. From here, if we say the probability of uninsured probabilities have to be between 0 and 1. Often their probabilities are reported as percentages, but for our math, we need the decimal, right? So the probability of being uninsured or a randomly sampled Texan is uninsured would be 0.255. From that, because there are only two options, we could also find the probability of someone being insured, right? The complement, 1 minus 0.255, which your brain, but I point to your heart, to your hypothetical heart, even though it's kind of here. I guess here, I'm old school. Right? So your brain does the complement already, right? You don't need the formula really, although it's nice to have. So we have the probability of being uninsured. Now, assuming that the uninsured rate stayed constant, what's the probability that two randomly selected Texans are both uninsured? Okay. And so now I have Texan number 1 and Texan number 2. Okay. I like to use my slots to solve these problems. And this Texan is uninsured and this Texan is uninsured, right? But in order for them both to be uninsured and uninsured, right? Remembering that and yields multiplication. When we say assuming the uninsured rate stayed constant, we're allowed to assume that they're independent. And in fact, by randomly selecting Texans, we're allowed to assume that they're independent of each other, right? And so that's what random sampling is all about. So I get the probability of the first uninsured, 0.255, and the second uninsured, which you can simplify as 0.255 to the power of 2, which is this guy here. Nice. Quick note on the difference between disjoint and complementary, because there's a subtle difference. Do the sum of probabilities of two disjoint events always add up to 1? Not necessarily, right? Because there could be more than 2 events in the sample space, right? And so just because if I roll a die and I know rolling a 1 and rolling a 2, those are disjoint, right? But those probabilities only add up to 2 and 6, right? I have to look at all the disjoint events and add all those probabilities in the sample space for them to add up to 1. Whereas by definition, if you have the sum of probabilities of 2 complementary events always add to 1? Yes, they do, right? Because you have the probability of A complement is 1 minus the probability of A. Right? So the complement is everything that's not A. There's a little trick I want to show you, And it's going to make our lives quite a bit easier later in chapter 4. And so that's why I want to introduce it here. But if we consider the scenario where we randomly select 5 Texans now, right? What's the probability that at least one is uninsured? Okay. Now it's that at least one or at least some small number that I want you to latch onto and kind of hang on to for, I guess, a couple of weeks. It's a big ask, I know, but it's nice to have seen it, right? So if we were to randomly select 5 Texans, then you have to be careful with your sample space, right? Because the number of Texans who are uninsured could be 0, and everyone always loves to forget about the 0, right? Pretty easy. You could sample 5 randomly selected Texans and they all have health insurance. That can happen, right? So I'm going to highlight the 0 here because that one is the one that's so easy to forget. Could be 1, could be 2, could be 3, could be 4, could be 5. Right? And if I've sampled 5 Texans, the number who are uninsured will be one of these, right, in the sample space. Now, when we talk about at least one, right, what are we really saying? Well, at least one is 1 or 2 or 3 or 4 or 5. Yeah? That's a lot of math that I'm saving you from. Okay, and so here, this 1, 2, 3, 4, 5, those are all satisfying the at least one criteria. So what we can do is we can just lump them up into at least one. Now what does this look like? This looks like a complement situation, right? And so here, one, or here I'll say at least one is 1 or 2 or 3 or 4 or 5. This would be a lot of math. You'd have to find the probability that 1 is uninsured. Yeah? But the problem becomes, well, it could be the first one, or it could be the second one, or it could be the third one, or it could be the fourth one, or it could be the fifth one. And then do the same for 2 and all of those different combinations, and it just becomes too large, right? And so here equals a lot of math that I don't want to do. So instead of doing that, what if I leverage the complement, bless you, and I say, okay, well, the probability of at least one must be 1 minus the probability of 0. Ah, that's nice, and that's true. So when we have this at least one, right, and it starts to look like a lot of math, whenever you have or, you're going to find the probability of each of these individual situations and then add them up. That's a lot. So we're not doing that until later. I know, sort of. But with our little trick with the complement, right, at least one, well, that's the whole sample space minus the probability that none are, right? We just take away that probability. I'm trying to remember that it's all in the slide so I don't write it all out. So we have the probability that at least one is uninsured becomes 1 minus the probability that none are uninsured. And so what does that look like? 1, 2, 3, 4, 5 Texans. And I want this one to be insured, this one to be insured, 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 insured. And this would give me the probability that none are uninsured. Uninsured. Right? They all have insurance. The probability that they have insurance in itself must be 1 minus 0.255. So this, the probability of I is 1 minus 0.255, which is 1 minus, oops, not divided, minus 0.255. I get 0.745. And if I multiply this through, right? They all have insurance with a probability of 0.745. Oh, I guess it's right here. Can't resist. Can't resist doing the math. Then I have 0.745 to the power of 5. Once I find that power, I can subtract it from 1 minus 0.23. I'm sure she's done some rounding. She's pretty sloppy with her rounding. And so 0.77-ish is the probability that at least one is uninsured. So remember this trick here. And I think you'll find it useful sometimes, right? Especially when you're staring down the barrel of a ton of math, right? Then you should start thinking about the complement. What if I found the complement instead and just took that away from 1? Just take away everything you don't want, right? It's a nice trick. Knowing that trick, roughly 20% of undergraduates at a university are vegetarian or vegan. What's the probability that among a random sample of 3 undergrads, at least one is vegan or vegetarian? Again, at least one. We're told that the probability of being vegetarian or vegan, which conveniently I'll just denote by a V, is 0.2. I'll do 0.20, a little cleaner. The probability of at least one V is 1 minus the probability of no vegans or vegetarians. So we need to find the probability that none of them are. Easy enough. The probability of no vegans or vegetarians is going to be 1, 2, 3 undergraduates, each with a probability of being vegan or vegetarian of 0.2, which means not vegan or vegetarian has a probability of 0.8 times 0.8 times 0.8. Oops. So I get 1 minus 0.8 to the power of 3. They didn't do the math, so we won't either. Oh. So using the complement to solve the problem makes it a lot easier. Okay. Any questions before we start our next section, which I was kind of hurrying towards, because it's a big section. Okay. 3.2 is on conditional probabilities. And so we've already seen conditional probabilities in the probability of A given B, right? We could read this as given, right? That vertical line. And what does this say? It's basically saying, well, knowing that B has happened, then what's the probability of A? Yeah. And so here, knowing B, I won't say has, okay, fine, I will. Has happened. It's not always the appropriate phrase, but I think it's nice for getting started. So knowing B has happened, what is the probability of B happening? Sorry, of A happening. Yikes. And that's the probability of A given B. We have conditional probabilities, right, in real life. If I tell you that, oh, stocks went up yesterday, right? That might tell you something about how stocks behave today, right? If they go on, well, these days, it's not as telling, but it used to be if they went up yesterday, they'll go up today, right? And if it was sunny yesterday, it'll be sunny today, right? There's some variation, but knowing that it was sunny yesterday tells us the probability that it'll be sunny today, or warm, I should say. Sunny, I don't know. It was sunny yesterday. As an example, we have this contingency table again, which we'll see a lot of, right? And so, and we've already done some work. Have you guys tried that, is it Florida voters that we're talking? That one's always, I always get questions about that one. So when you get to the Florida voters, you'll know. And it can be a little bit tricky. And I always have tons of questions about that one. This one, believe it or not, is similar, even though it doesn't really read that way. So researchers randomly assigned 72 chronic users of cocaine into 3 groups, risque. Desipramine, which I never know how to say, so I just kind of wing it, which is an antidepressant. Lithium, which is the standard treatment for cocaine, and then placebo. Placebo, of course, is just a sugar pill, and you tell the patient, hey, here's this miracle cure. You're going to feel so much better. And then you map the results, and that's how we get the placebo effect, right? Where we see positive results in the group taking the placebo, right? What does that do? It kind of discounts the other group taking any sort of treatment if they end up being the same, right? You could just tell someone, oh, you're getting this amazing treatment. Oh, wow, yeah, I feel so much better already, right? And so that's an effective treatment a lot of the time, actually. So what we're mapping is whether they relapse or they don't relapse. Okay. And so we've got this, the antidepressant, right? And we had 24 in the antidepressant group, 24 in the lithium group, and 24 in the placebo group. In experiments like this, it's pretty common that we just assign evenly into the groups, right? But it's not necessary. And we can have uneven groups, but in experiments, we tend to kind of force it if we can. So then we record, okay, how many relapse after some amount of time, right? And so, well, overall, 48 out of 72 relapsed, okay? For example. I guess I knew what was coming. Yeah. First, I want to point out that these totals are the margins. Okay. So sometimes we call them marginal probabilities when we're ignoring the breakdown inside. Okay. And so what's the probability that a patient relapsed, right? There's no breakdown of a subgroup, right? And so then I'm looking at a total of 72 patients. How many of those relapsed? 48. And so here we have the probability. If I call this R, then usually what we do is we call this not R, right? Or the complement of R. I like to call it not R just to emphasize that it's the opposite, right? But if you want to call it the complement, that's great. Whenever you can, split things into a positive like this, R, and then the negation of it or the complement of it, that'll make your problem solving a lot easier. Okay? Instead of trying to assign a new name for the second group. But we were asked to find the probability of R, which in this case is 48 out of 72. We can 48 over 72. I get the probability of relapse is roughly 0.66666 repeating. We can round it to 0.67 or so. So these probabilities that we find for the overall groups are called marginal probabilities. I've got it covered here, marginal probabilities. Okay? As opposed to joint probabilities. Okay? Now, joint probabilities are probabilities inside here. Okay? They're joint between the two groups, or the two variables, I should say. Such as, what's the probability that a patient received the antidepressant and relapsed? Huh? We'll call this the antidepressant, the lithium, and the placebo, let's say, just for shorthand. Right? I don't really have an easy A, not A situation, although I could lump the lithium and placebo, but I don't want to do that. And so what we want to find, if this is R and this is the complement of R, what we were asked to find is the probability of, the antidepressant, which, let's call it D instead, just so that they match. Sorry. D and R. Not D and R. Do not resuscitate. D and R. I watch too many gory shows, I think. Not gory, but like crime shows. They signed a D and R. Anyways. The probability of desipramine and relapse of any patient is 10 over 72. Which I'll wedge in here. Should be 0.138 repeating. Now this example is from a slide later on, but I wanted to bring it up here and then we'll kind of skip some slides because it gives away the answers and I want us to work through the answers. But if you read this example compared to this example, right, there's some subtle differences in the question, right? So if we know that a patient received the antidepressant, desipramine, what is the probability that they relapsed? Okay, so here we know they are in the DESI group. So we're told that, well, that really narrows down the group of people that I'm talking about, right? And in terms of formula, what does this translate to? This is the probability. I want to find the probability. What is the probability that they relapsed, right? So I want to find the probability of R knowing that they were in the D group. Well, when you put it like that, easy enough. Well, not yet, because it's our first time really working with this formula, right? But you do remember on your formula sheet, you have something that looks like, can I put it as a reminder? I'm running out of room here, but I do want to keep them on the same. Remember, the probability of A given B is the probability of A and B divided by the probability of B. Mapping my R to be A's, so wherever I see an A in the generic formula, I replace it with an R. And wherever I see a B in the generic formula, I replace it with a D, right? How I tend to read it is I tend to read it as the first one and the second one divided by the second one. Which makes it easier. Then you don't even need to look at the formula sheet with practice. Right? So if it's the first one, so if it's the probability of R and D, divided by just the general probability of the second one, one thing to keep in mind is that the probability of R and D is the same as the probability of D and R, right? Because it'll still be 10 over 72. So it doesn't matter which order in the ands, right? A and B is the same as B and A. So just to match what we have here, I would say this is the same as the probability of D and R divided by the probability of D. Now what's nice is we have all these components, I think. No, we found the probability of relapse. That's okay. What if up here, because I'm running out of room, I want to find the probability of D, which I'll need. Well, the probability of being in the desipramine group is going to be 24 over 72. Now you can use the fractions, or you can use the decimals if you prefer. There's a lot of repeating decimals though. So in that case, I would encourage you to try to use the fractions, right? But you don't have to. As long as you make sure you don't do any rounding in your calculator, you can still use the decimals if you want to. I'll show you with the fractions though, they're not too bad. The probability of D and R was 10 over 72. And we just said the probability of D, if I can remember, 24 over 72. Remember fractions? Fraction over a fraction. You have to flip the denominator and multiply. What's really nice is we get to cancel some stuff. So we get 10 over 72 times 72 over 24. And I get 10 over 24, which is probably still nothing nice. It's not. .416. Repeating. Whee! Which means that the probability that they relapsed, knowing that they were in this antidepressant group, is roughly 42%, right? Or 0.42. Which is different from the overall probability of relapse. Okay? So that's a good sign. Yeah.
Where we just take the relapse from this, I mean, multiply by the total in that grouping.
So what you can do, I wanted to show you the formula way, because the formula way will always work. But I suspect what you mean is, okay, well, if I know that they're in the desipramine group, doesn't that restrict me to here? I think is what you're getting at. Yeah, and it does. And that's, you can totally answer it this way too, right? So then it restricts me to this 24 as my total, and I'm interested in these 10 out of the 24, which is the same answer. And yeah, it is quicker, but at least with the formula, it'll always work. How's that for a selling feature? Very slow, but it'll always work. But yeah, you can. If you have a contingency table, you won't always have a contingency table, but most of the time you will anyways. So, okay. And then this slide, we just did it. And this is the one that I stole from, so I'll cut it. This one was just a repeat for some reason. You can do the same across the three groups, right? So knowing that they were in the desipramine group, oh no, they're looking at the probability of relapse. No, the probability of being in a group, knowing that they relapsed, which is slightly different. Right? So if we know that the patient relapsed, I shouldn't have gone so quick. What's the probability that they received the antidepressant, desipramine? So then if we know that they're in the relapse group, right, that restricts us to this 48, and then we can find each of the probabilities. Yeah? Now this looks a lot simpler than the Florida voters, but it's the same idea, right? And so of this subgroup, then what's the probability, right, of something? Now, when we compare these groups, knowing that they were in the relapse group, we see quite it feels like some variability in the probabilities, right? And it looks like these were slightly improved over the placebo, and so that's good, I guess. It's always what you're going for. Okay? And so here, since these probabilities are quite different from each other, we suspect a treatment effect, but we have to wait to learn how to determine it for real. But the suspicion is a good thing to start with, right? Why do we think that these are different, a treatment effect? Meaning, just depending on what treatment you receive, right? That will determine your probability. Okay. Good. So these are all conditional probabilities, right? And that's how we get to the general multiplication rule. Right? So if A and B are two outcomes or events, then the probability of A and B is the probability of A given B times the probability of B. Right? And we've used, or we've seen, the probability of A given B is the probability of A and B divided by the probability of B. So then all I've done is multiplied this probability of B over and said the probability of A given B times the probability of B is the probability of A and B. So it's just a special case. Probability of A and B is the probability of A given B here times the probability of B. Right? Now you're allowed to use it even if they're not independent. That's nice, because then you've incorporated this conditional probability. Right? So we can use this. We can use this even when A and B are not independent. We've actually already seen this in action. We never called it something like this, but as a quick example from last day, remember when we were drawing cards and we had the first card drawn was an ace? And then the second card drawn, what's the probability that the first two cards drawn are both aces, right? We made that adjustment knowing that the first card was an ace, right? And so the probability that two cards are aces, we said, well, we solved like this. A, for my first card, I'll use A1, right? I have 4 aces in a deck and I have 52 cards because I'm just starting out. And so here I have 4 and 52. And now I need the second card to be an ace. Remember what we did? We said, well, now there's one fewer cards. Usually we're pretty good at remembering that, which means that my total must be 51. Oh. And I've already drawn an ace previously, so I use that information and I say, well, then that must be 3 over 51. And then we said we multiply these because one has to happen and then the other one has to happen. But what does this translate to? This is the probability of, can I use A1? Just Oh yeah, A1, AI, so funny. I'll call it A1, ace on the first draw. All right, shorthand. What's this? This little guy is the probability of drawing an ace on the second card, knowing, given, that we drew an ace on the first card. We didn't call it that, but we kind of got to conditional probabilities on our own, right? We said, well, I gotta adjust the number of aces and the number of cards. Those are conditional probabilities, right? And so here, right, even though they're in a different order, right, the conditional probability times the probability of B, well, it doesn't really matter, right? And so how I can rewrite this is the probability of A1 and A2 is the probability of, gets a little, wait, especially when I flip around like that. Or it's not me, but is that the Zoom?
Okay. Whoops, get tangled up. Thank you.
There you go. Should just mute everyone, but it doesn't. It never does. Anyways, that's all right. Gets a little bit tricky, right? Kind of learning, okay, A and B is the same as B and A, right? So then I'm allowed to swap the order of A1 and A2. But if you spend enough time kind of staring at this, then you'll see that this is just a version of this, right? A's and B's and conditionals, right? Growing up, if I had math homework, so my dad's a software engineer, and so of course he does a lot of math. And if I needed help with math, he really was the type to be like, well, just squint harder. He like could not understand that I couldn't understand it. He's like, just look at it a little bit more. So I guess I did get there. But now that's all the advice that I have. Just look at it a little bit harder. That's not all. But sometimes you just have to spend time with it, which is what he could have said, but he didn't. Quick note on independence and conditional probabilities. When I look at this, even without knowing the situation, which I guess we should do, consider the following hypothetical distribution of gender and major of students in an introductory stats class. So if I ask you, are you in a social science or not? Right, just kind of create two categories, right, in which we do a lot. That's kind of a trick that we use. Yes or no, right? Lump everything else into the nose. So then if I'm looking at these probabilities here, it looks like the counts across the majors in each of the genders is the same, right? So what does that kind of lead me to believe, right? Tells me that knowing the gender doesn't tell me anything about the major, right? We can confirm that with formulas, but it's kind of a special case, and so I don't want to spend too long here. If we call the social sciences just S, usually we only like to use one letter, but then the I guess we could use S and N or something. I don't know, doesn't matter. The probability that a randomly selected student is a social science major, right, is going to be the 60 out of 100. Right? So we can find that probability and call it the probability of being a social science major. Now, the probability that a randomly selected student is a social science major, given that they're female, so knowing that they're female, they're in this group of 50, right? Then 30 of those are social science majors. And so the 30 over 50 is still 0.6, which we can write in probability notation as the probability of SS given F. Then if we look at the males, right, the probability of a social science given their male is also 0.6, right? 30 over 50, all these numbers are the same. So then what we conclude is that the major of the students in this class does not depend on their gender, right? So knowing if they're male or female doesn't change the probability of being a social science major, right? And so that's, by definition, they're independent, right? So here I'll say, therefore, they're independent. So that's what it would look like if they were independent. Of course, we introduced last day, if the probability of A given B is just the probability of A, right? It doesn't care about B happening. Okay? Then the events A and B are said to be independent. Okay? And so giving B doesn't tell us anything about A, and there's lots of things that are independent, right? Knowing that I drew an ace doesn't affect the probability of rolling a 6, right? They're independent of each other. Can still happen. Right? I drew a card. Okay, doesn't matter. So if they're independent, so if A and B are independent, then we can say that special case where we started earlier today, right? The probability of A and B is the two just multiplied because the probability of A given B is just the probability of A. Okay, before we do this example, well, first I want to ask if there are any questions. A common way to solve probability problems is using what we call a tree diagram. Yeah? And so a common way, I'll say, to visualize and solve probability problems. A lot of probability problems, in fact. So I'll say probability problems is using a tree diagram. Is using a tree diagram. It's especially useful if you can reframe something as event 1 and then event 2. Right? And so I'll make a subnote here. Trees are especially useful if we can reframe the problem as 2 consecutive events. The example that I like to use is if in a course you write a midterm, and then you write a final. Right? That's a likely kind of two consecutive events scenario. So as an example, in a course, you write a midterm and a final exam. Let's say first, I'm gonna let M be shorthand for getting an A on the midterm. Okay? So here, you get an A on the midterm. So you write the midterm and you either get an A or you don't. Yeah. Reframe. But it was a little shaky, wasn't it? Well, here we go again. Reframe. Reframe. So if I let M be getting an A on the midterm, awesome. You got an A on the midterm, what's the other option? You didn't get an A on the midterm, right? And what if I let F, kind of ironically, I guess, be you got an A on the final? Because if I use A, then it gets boggy, right? And you want to try to only use one letter, right? M-A-F-A, you could do that, but it gets kind of confusing. Now, to introduce this tree diagram, I'm going to draw it, and then we're going to talk about it. And so it might look something like this. First thing, just in general, you have your first event denoted by 2 branches. Now, I like to do my tree, I guess it's kind of an upside down tree. I like to do it from top to bottom. You'll see in the textbook, they do it beautifully like this, kind of off to the side. I find it's easier to read, of course, but I find that it's hard to set up. So I like to kind of give myself lots of space for the first set of branches, because then we'll have another set of branches for the final exam off of each of these branches. So it's going to look like this. Your first event, followed by your second event. So I call them kind of 2 layers, essentially. Now your first event is the midterm. First you write the midterm, and you either get an A or you don't. So I'll write M or the complement of M. What if I tell you, all right, the probability that a student gets an A on the midterm, what is it? I'll make it up, is 0.7. Pretty good. What does that mean? Means the probability that you don't get an A on the midterm must be 0.3. So what we'll notice is that a set of branches has to add to 1. So each set of branches must add to 1. Yeah. All right. The second event, in this case, would be the final exam. If you got an A on the midterm, what are your 2 options? You could get an A on the final or not get an A on the final. Same thing, if you didn't get an A on the midterm, you can still get an A on the final or not get an A on the final, right? These probabilities will be conditional, usually, on what happened in the midterm, right? Just kind of intuitively, do you think if you got an A on the midterm, the probability of getting an A on the final should be a little bit higher, right? Traditionally, right? And so then, but not always, then let's say, I'll use light blue for this guy. If you got an A on the midterm, so now I know you got an A on the midterm. The probability that you get an A on the final shoots up to 0.9. Yeah. Remembering that each set of branches must add to 1, then the probability that you don't get an A on the final must be 0.1, right? Because if you got an A on the midterm, you're in this group and you only have these two options, right? A on the final, not A on the final, right? So these have to add to 1. What are those probabilities? Those are conditional probabilities, right? I just don't bother writing them like conditional probabilities. Technically, this is the probability of F given M. But usually I skip writing that out. So then it's understood that these probabilities that I write are conditional probabilities. But it's the reason we use these tree diagrams is because it makes it a little bit easier to visualize the problem, but also to solve it, and you'll see. If you didn't get an A on the midterm, then I'll give you a 0.6 probability of getting an A on the final. Yeah, that's pretty good. Which means the probability of not getting an A on the final must be 0.4, right? And again, this is the probability of an A on the final given you didn't get an A on the midterm, right? Technically, those are all conditional probabilities. But it's understood that once you have your branches, right, then the next branch has to be the conditional probability. Okay? You can even use tree diagrams for independent events, right? You flip a coin, that's boring, but you flip a coin, heads, tails, probability 0.5, probability 0.5. Flip a coin again, the second event, heads, tails, becomes a very boring tree diagram, right? Something you can solve without it, but you can still use a tree diagram. Now, what's the benefit of a tree diagram? At the end, if you multiply down each of the branches, what you'll find is the probability of M and F. Okay? Then you'll find the probability of M and not F. Okay? Now, my shorthand is pretty sloppy, so usually I just make a little note to myself what the combination is at the end of each branch. Okay? Technically, what I'm saying is this should say the probability of M and F, which we know is the probability of M times the probability of F given M, which is 0.7 times 0.9. But notice that's just multiplying down the branch, right? So 0.7 times 0.9. Oops, not, yeah, good. Is I get 0.63. So what we do to find the probabilities at the end of each of the branches, which are all the unique combinations that we could have, we multiply oh, let's say down the branches to find all the, can I call them and probabilities of the unique combinations. It's also a nice way to outline what all the possible unique combinations are. And so at the end of each branch, like I said, I like to do a little reminder of what the combination is at the bottom of each branch. And so I just read it M in the complement of F, not M, F, and not M, not F, or the complement.
What's the word before combinations?
Unique or unique. I can't even read it. Unique. I think if I was using the Apple Notes, it can clean up my writing. It's a reason to use it. But I think most of the time it would be like, what do you mean? What do you want from me? So instead of showing all this work, usually what I do is you can just multiply down each branch and jot down what the number is. Okay? Making sure you don't round unless you absolutely have to. And there's a reason for that. Can you guess what it is? These are all the possible combinations, which should add to 1, right? If you've done things correctly, they should all add to 1 once you consider all of them together, right? So that's why you don't want to do any rounding unless you absolutely have to, and then give yourself some wiggle room if you have. 0.7 times 0.1 is 0.07. 0.3 times 0.6 is 0.18, and 0.3 times 0.4 is 0.12. Just as before, right? Each set of branches must add to 1. So now this is a new kind of set of branches, and these must add to 1. Oops. I use it just to check my work, right? If I didn't do any rounding and I did it all right, then I can add these up. I have 0.12 plus 0.18 plus 0.07 plus 0.63. Phew, I get 1.
But that doesn't matter for the Fs.
No. So, excellent segue. Now, or sorry, let me clarify something. Do you mean this F and this F?
Yes.
So the first event, right, you got an A on the midterm or you didn't, that splits you up, right? And depending on what happened on the midterm, right, that will determine the probability of getting an A on the final. But I think what you're getting at is, as an example, find the probability of getting an A on the final. Maybe, sort of. Now, I just want the probability of F, right? But there are two ways to get there. So I want to go through all my scenarios where I got an A on the final, right? And so I see that, okay, I could have gotten an A on the midterm and an A on the final. That's one of the ways. Or, right, catch yourself saying or, because that means you're going to add these probabilities, right? And so, or you didn't get an A on the midterm, but you did get an A on the final, right? So now there are two different ways that you could get an A on the final, okay? Regardless of what happened on the midterm. Okay? And so what we find is that the probability of an A on the final, just blank, is going to be the same as the probability of an A on the midterm and an A on the final, plus the probability of not an A on the midterm, but still an A on the final. Okay? Because you're saying or, right? This first highlighted branch or the second highlighted branch. Okay? And so if you've done the work and you've got all these probabilities written down, then you can just go ahead and grab them from the tree, right? 0.63 plus 0.18. Hmm. 0.63 plus 0.18 is 0.81. So the probability of getting an A on the final would be 0.81 or 81%. Ew, that's pretty good. I think I know what you meant. Or did it answer it? Can let it play a little bit longer next time. Here, these branches are still split up, right? So they're not the same set of branches yet. Once I consider the full set, then all of a sudden they become one set of branches again. But here, so here they add to one, and here they add to one. But they're still considered separate. Or this is the only one you really need in order to check your work, right? Those should all add to one. Okay, how am I doing? Actually pretty good. So let's do a tree diagram, a proper one, not one I've made up. Any questions about tree diagrams before before we do a big example? Okay. Like I said, that was just our first one, and I kind of used a tree diagram to illustrate what a tree diagram is. But now we have kind of a proper example to work with. Yeah? So breast cancer screening. The American Cancer Society estimates that about 1.7% of women have breast cancer. So a very low percentage. And blah, blah, blah states that mammography correctly identifies about 78% of women who truly have breast cancer. And so if you have breast cancer and you do a mammogram, then it'll catch it about 78% of the time. Not super high, right? But I guess it's as good as it gets. An article published in 2003, hopefully they've been doing work on this stuff, suggests that up to 10% of all mammograms results in false positives for patients who do not have cancer. And so what we can do is we can set up this, this tree diagram. We don't have a question yet, but I want to spend some time picking out our tree because that's going to help us solve any question. And so here, let's construct the tree diagram. For the probabilities above. At first, this is really our first example, in terms of formulating this tree in terms of a first event and then a second event, right? I'm going to say the first event is you either have cancer or you don't, okay? And then we do a test, right? Another way to determine which one is your first set of branches and which one is your second set of branches is that this 78% is conditional, right? It's conditional on, well, those who actually have breast cancer, right? And so here we're given they have cancer. We'll just kind of cancer broadly, breast cancer, of course. So if it depends on if they have cancer or they don't, then that means our first set of branches must be, well, do they have cancer or no? Right? And so my first set of branches, I'll do like this. And you want to give yourself as much space as you can. Okay? And, oh, I guess I should define my variables. First, we're going to let C be the patient has breast cancer. Which means the complement of C is they don't have breast cancer. I'm going to use a plus for a positive test. Positive test means that it says that you have breast cancer. Right? Now, of course, if you have cancer and you get a positive test, that's a good thing, right? It's bad if it misses it, right? But if you don't have cancer and you get a positive test, right, that's actually a bad thing, but it's better to be safe than sorry, right? And so that's where we get our false positives from. And so in terms of medical testing, we usually use a positive group. So testing positive. And I like to use, so I will use negative instead of the complement of a positive, because we have a symbol for the complement of a positive is a negative. right? And so that's what I tend to use. But if you want to just stick with the complement, totally fine. Huh? Okay. So if you have cancer, you can either get a positive test or a negative test. Huh? Same thing. If you don't have cancer, you can potentially get a positive test or a negative test. Huh? Now we were given the probabilities for each of these in the blurbs. Let's start here. 1.7% of women have breast cancer. Huh? And so that means that, and for our math, we have to use the decimal version, right? So 1.7%. You want to be really careful. Sometimes there's a percentage button, but I think that converts it to a percentage, not out of a percentage. Let me try it. 1.7. Oh, it did. Or you can just divide by 100, of course. But it did convert it to a decimal. Oh, that's nice. Things I didn't know. 0.017. Oh. Which means the probability of not having breast cancer must be 0.983. So very high. Right? Not one, but high. Let me clean that up. Okay. We've dealt with this one. Now on to the next one. If it correctly identifies about 78% of women who truly have breast cancer, right, then correctly identifying someone who has breast cancer must be a positive result, right? So you kind of have to think about that one, but a little bit of convincing yourself, the probability of getting a positive result given that you do have cancer is 0.78, which means the probability of getting a negative result is 0.22, which in my opinion is quite high, bad. Okay. Up to 10% of all mammograms result in false positives for patients who do not have cancer. So a false positive has a probability of 0.1 for patients who do not have cancer. You get a positive 0.1 for 10% of the time, which means you get a negative 0.9. Okay. Now, what I like to see is I like to see all the combinations just written at the bottom here. You don't have to use the probability notation. It's kind of understood, and then calculate each of those probabilities. And so here I have cancer and positive, cancer and a negative test, not cancer and a positive, not cancer and a negative. And if you multiply down each of the branches, here we go, 0.017 times 0.78. And you want to keep, I know there's a lot more decimal places when I didn't make up beautiful numbers, but you want to keep them all. As long as they're not repeating, just keep them all as much as you can. 0.017 times 0.22. Of course, my calculator does scientific notation. 374. Let me just count. 1, 2, 3. Okay. 0.983 times 0.1. I get 0.0983. And finally, 0.983 times 0.9. I get 0.8847. Add these all up just to make sure they add to 1, so nothing went wrong here. 0.0983 plus 0.00374 plus 0.01326. Phew. Sum is 1. Bink. This I can't even read myself. Right. Add those all up, should equal 1. Okay, good. Now we have all the probabilities that we could possibly want in order to solve any problem. So let's see what our question is. I'm going to bring it up here because we've got all our work done here. So when a patient goes through breast cancer screening, there are 2 competing claims, right? The patient had cancer and the patient doesn't have cancer, or has cancer maybe. If a mammogram yields a positive result, what's the probability that the patient actually has cancer? It's good to know, right? Especially if you're doing these tests. Huh? Now, we no longer have the contingency table, so we have to use the formula. And so now I want to translate what I'm given, right? So I want to find the probability of cancer given that they had a positive result. So I know they got a positive result, then what's the probability that they actually have cancer? Huh? We're getting used to reading this conditional probability, right? And so we've got the in our numerator, we have the probability of C and positive, right? Divided by the probability of a positive result. Here we go. The probability of C and a positive divided by the probability of a positive result. Can use the tree. C and a positive, I already know that that probability must be 0.01326. Huh? So you're allowed to just punch that in, 0.01326. Now, what's the probability of a positive? That's the same thing as what we saw. Well, what's the probability of getting an A on the final exam? Well, there were 2 ways of getting there. Same thing with getting a positive result. You could come down the first branch, right? Or you could not have cancer and still test positive, and that would also give you a positive result. Right? So, cancer and positive, or not cancer and positive, right? Which means that the probability of just testing positive is the probability of cancer positive plus the probability of not cancer positive. Or if you prefer, 0.01326 divided by, I'm gonna try to keep it all on the same page, but I can't write properly. 0.01326 0.1326 plus 0.0983. It throws a lot of people off that you have the same number in the numerator and the denominator, but because these are being added together, they don't cancel, right? And so you want to be careful of that. So we have 0.01326 plus 0.0983, just to highlight that we do get a number. 0.01326 divided by 0.11156. 0.01326 divided by that previous answer. I get 0.118859806.4. Or roughly 12%. Very roughly. I'd probably go for 11.9%. But I'm pretty sure she uses it later in an example at 12%, so I don't want to throw you off. Trying to remember that far out. So the probability that someone actually has cancer, given that they test positive, right, is going to be 12%. Huh. All right. That's good to know. Right? And that 12% is not obvious, right, from any of this information. Right? So we had to do all that work to get there. Okay, nice. Here, she's done it so beautifully. But we already did it. We already did it all together. So this is all just the same. How about this one? Suppose a woman who gets tested once and obtains a positive result wants to get tested again. Huh? In the second test, what should we assume to be the probability to this specific woman having cancer? Now we have to adjust that initial probability to 0.12, right? Because we have this first positive test. And so really we would I shouldn't say just, we would not just adjust, there we go. We would have to adjust this probability and amp it up to 0.12, which means this probability would be what, 0.88 math. 1 minus 0.12. These probabilities would stay the same, right? Because they're still test probabilities, but now we have amplified the probability that she has cancer because we have that first test. So here, we know the probability of having cancer given a positive test is roughly 0.12. So then we'd have to make an adjustment. No? Let it simmer?
Well, you said that the first numbers would have to be changed. But where did you get the numbers from that they're changing into?
So this probability that we found is for the first test. Don't worry. How about this one? What's the probability that this woman has cancer if the second mammogram also yields a positive result? Do it again. I will cheat a little bit in the interest of time. And again, I'm gonna just copy. These probabilities will change slightly. So now, let me just erase this all here. Oh. I'll erase the highlights. Hey. And the sub. Now, we know she had a first positive test, which means the probability that she has cancer, we adjust it to be 0.12, right? Now, it decreases the probability of not having cancer, which is not a great thing, is it? To 0.88. Now, if I multiply down these branches, what do I get? I get 0.12 times 0.78. I get my new probabilities, 0.0936, 0.12 times 0.22, 0.0264, 0.88 times 0.1, just multiplying down the branches, 0.088 and 0.88 times 0.9, 0.792. I'll just confirm that they add to 1, plus 0.088, plus 0.0264, plus 0.0936. They do. I'll just say equals 1. Dink. So now we want to solve the same problem. What's the probability that they have cancer given that we have a positive result again, right? With these adjusted probabilities. So again, we're interested in those positive results. So we want to find the probability of cancer given a positive result, which is the probability of C and a positive result divided by the probability of a positive result. And maybe I'll do it, which is the probability of C and a positive result divided by the probability of C and a positive result, or the probability of not C and a positive result. Takes longer for me to say it than to write it, I think. I get 0.0936 divided by 0.0936 plus 0.088, which I'll move over here. 0.0936 plus 0.088. 0.0936 divided by 0.1816. We're so close. 0.5154185022, or roughly 0.52. Which speaks to the benefit of retesting, right? And it makes sense. If you get a test and you're not 100% sure of the results, right? You should test again. Then all of a sudden, okay, now you've had 2 positive tests in a row, right? The probability all of a sudden is more than 50%. You can do it with a third test, right? Just to be sure, which is probably what they do, right? Then what would you do? Do the same thing again, but adjust this from 0.12 to 0.52 and 1 minus 0.52, right? Do all the math again. And then eventually, after some number of tests, you would be very sure that they actually have cancer. What we just did is technically called Bayes' theorem. I'm never going to call it that. And so it's this fancy theorem, but as long as you understand the tree diagram, I'm happy. I'm going to let you try this one on your own. I'll post the solutions, because it's quite a big example and we won't have time to do it next week. Hold up. I need more, just a little bit more time. Hey, I got 3 minutes. Come on. And then you'll be free of me for a week. It's pretty good. So I'll let you try that one. I'll post the solutions in the notes before I post them. And of course, the answer is in here as well. So I guess you don't really need it. 3.3 and 3.4, we're not going to do. So my question to you, do you want, I have assignments for them. Do you want a bonus assignment? So you can read it if you want to and do the assignment and replace a lower assignment grade, right? I'll just set the assignments to drop however many bonus assignments we do, which is usually, I don't know, 3 or 4, could be 4 now, right? So let's do that. I'll post it as a bonus assignment. Try it. No harm. If it's your lowest assignment grade, it'll just get dropped anyways, right? Enjoy your sort of long weekend. See you in a week. Yeah, you bet. Let me just stop this here.